Hello everyone, my name is Geraldine Osorio in AP Chemistry with Miss Foley, and today we're going to be talking about atomic structure, and we're going to talk about things ranging from the atom itself and people who discovered it to electrons and being involved in the wave mechanical model. So to start off, I want to ask a few questions. So what are subatomic particles? Now, we know them from first, second, third, fourth, fifth grade as protons, neutrons, and electrons. Give me a second, let me write them here. Right? And I have a second question. Well, where are these subatomic particles located in an atom? You may know that electrons usually go around the atom and protons and neutrons are in the middle. Well, what are the specific names of these locations? We'll go into that later with the rest of the lesson. And last question before we start. Give some characteristics for each subatomic particle. Now, as little kids, we all know that protons are positive, electrons are negative, and neutrons, well, they're just neutral. And what does this mean? Protons have positive charge, electrons have negative charge, and neutrons have no charge. We'll get a little bit more in depth into that later on, but for now, let's keep on going. So, the atom. Major discoveries were made by scientists such as Robert Boyle, who identified the gold and silver as being elemental. This was extremely riveting and advancing in the science world because at this point, these precious metals weren't considered elements. So, next we have John Dalton, who theorized that the basic unit of matter is a tiny particle called an atom. This guy basically is who started what we're talking about today. John Dalton. He's the big kahuna. I don't even know if that's the expression, but yeah, he's very important. Then we have Mr. John Dalton again with his atomic theory. Now, just to specify, Dalton's atomic theory is very long and drawn out, so he has a completely separate slide just for his atomic theory. So if you're taking notes currently, you put down major discoveries under a big bullet, as an umbrella bullet basically. Then as sub bullets or as little sub points, you can put down Robert Boyle with identifying gold and silver as being elemental, John Dalton theorizing that matter is made up of tiny particles called atoms, and then put another sub bullet underneath John Dalton that has 3 stars next to it, next to his name. So basically 3 giant stars because he's super duper important. Next slide. So, the atom. I already explained this slide a few minutes ago, but I had technical difficulties, so I had to begin recording again. It's okay though, we can just explain it again. So the atom, basic building block of life, how important. Oh, I love the atom. Whew, science. So, major discoveries were made by scientists Robert Boyle and John Dalton. This guy, same person. I just had him separate. I don't know why, but he is separate for a reason, and let's just leave it like that. So these two are the same person down here. Don't worry about them. They're not separate. I'll explain in a minute. So Robert Boyle, he identifies gold and silver, which were precious metals at the time and regarded only as precious metals, as being elemental. So Robert Boyle is attributed to elemental gold and silver. Okie dokie. Now let's get into John Dalton. Basically what we have under him as a discovery is theorizing that the basic unit of matter is a tiny particle called an atom. So he basically developed atomic theory. And we keep his name separate down here because his atomic theory is crazy important. Like, you need to know it so well for the Regents, not only for the Regents, but for any other type of chemistry you'll ever take. You need to know Dalton's atomic theory. It's like the foundation of chemistry, basically. But we'll explain that on the next slide, I believe. So let's keep going. Boop, 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 boop. Where the heck is the slide? Technical difficulties. Here we go. So, Dalton's atomic... Whoa, that was gross. Dalton's atomic theory. I apologize if you can hear me swallowing. I really do. I just got back from Six Flags today, so my mouth is like super dry, and my PowerPoint got like broken in sending it from school to my email and stuff. So now I'm recording again at 9 o'clock at night. Woohoo! And it's due in like 3 hours. But it's okay. So, Dalton's atomic theory. All elements are composed of indivisible atoms. Let's write that down in our notes. Indivisible. What does that mean? That means that they cannot be broken down anymore. What are these? Subatomic particles, because elements composed of atoms can't be really divided any further, because otherwise you'll just have a bunch of atoms of the same element, which is basically just the element. So you can't really subdivide an element because it's just made of one composition. And if you look at it in retrospect, it's like if you have a piece of bread. This is a really funny example, but if you have a piece of bread, if you cut up the bread into 2 pieces, you have 2 pieces of bread, which are each bread. So technically you didn't really make a change, you just split the bread and made more bread. Didn't make more bread, but you know what I mean. Okay, next bullet. All atoms of a given element are identical. Now, what does this mean? So, elements have identical atoms, which gives them the property of being an element. Just as the bullet before said, they're indivisible. So, its makeup has to be uniform in order for it to be a pure substance. Elements are pure substances. Remember that. So, atoms of different elements are different in their masses. Atoms of different elements obviously are different, but they're also significantly different in their masses. Not only that, but their atomic number, and this attributes to the mass number. So basically, all you need to know is that in the periodic table, when an element changes, it's usually because its mass is changing as well. So if its number of protons changes, its mass automatically changes. If its number of neutrons changes, its mass automatically changes. It's all dependent on mass, basically, of certain aspects of the atom, but overall just relatively on mass. Compounds are formed by the combination of atoms in different elements. They are in fixed ratios. Everything is proportional. Conservation of mass. Woo! Conservation of mass, matter, and charge. Always. Always. Oh my goodness. You don't know how important this will be later on in physics, in AP chemistry if you decide to take the course, in anything, even in Regents chemistry. Always remember that charge, mass, and matter will always be conserved. Always, 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 always. Alrighty. Let's continue. The structure of the atom. Okay, so electrons. J.G. Thomson uses this is a crazy important experiment, a cathode ray, to show electrons. A concept of the atom was developed in which these particles, which were negatively charged, that's supposed to be a minus sign, negatively charged, were visualized as being embedded in atoms, compared to raisins in bread. This is supposed to say embedded. So why are they compared to raisins in bread? Basically because the raisins inside a piece of bread are within it rather than along with it. If you bite into a piece of bread, like if you bite into a piece of cinnamon raisin swirl bread, you're not going to be able to pick out the raisins all from the surface because there are some that are baked within it. That's basically what this was trying to say, that the electrons were within the atom and they couldn't really be removed. But we find out later on in history in general, that electrons can be removed through ionization and through bonding, whatever. That's besides the point. But J.J. Thomson, one of the beginning discoverers, I don't even know if that's a word, discoverers of an atomic model in which the electrons are embedded within the atom. This model is also known as the plum pudding model. I'm assuming plum pudding because it was popular at the time, and when you put plum in pudding, you can't really pick it out all the way. I don't understand, but that's just what it's called. Oh, also, the Regents likes to refer to it as that, so do not forget this term. Very important. Plum pudding. Now to the nucleus. Ernest Rutherford directs alpha particles, which are positively charged particles that are much smaller than an atom at a thin piece of gold foil. This experiment is also referred to a lot within the Regents curriculum, so remember it. Directs alpha particles. Let's write it in blue. Let's erase, actually. Alpha particles. Alpha particles, which are positively charged particles, typo, that are much smaller than an atom at a thin piece of gold foil. Most particles within the experiment passed straight through and were only slightly deflected, and this basically proved that the atom was made of mostly empty space, because if alpha particles, which are smaller than atoms, were shot through an element which is composed of only one type of atom, it's basically saying that the positively charged particles weren't really deflected by the positive charges within the nucleus at all, proving that there's a lot of empty space for particles to go through and run through. The ones that were deflected because of repulsion, because of positive charges within the atom. So basically imagine like running through a football field, and within the football field there's little tiny circles where the players can run around in little circles. And if you run through it, if you're not really paying attention, once in a while you'll bump into a football player and maybe get knocked down or get thrown off course. But if you're looking up, you can run through them, basically through the empty spaces, and that's basically what was happening here. The alpha particles were running through the empty spaces, and sometimes they weren't really paying attention, not literally, but in the sense of the example, weren't really paying attention, and maybe they bumped into one of the football players, and then they got deflected, football players being a positive charge in this case. Okay. Most particles passed through passed straight through, and few were deflected. The nucleus must also be positively charged because like charges repel each other. This experiment, the gold foil experiment, determined that the atom has a positively charged nucleus surrounded by electrons, basically. Okay. Protons and neutrons. Protons are positively charged particles, and neutrons are neutrally charged particles, obviously stemming from the names, positive, neutral. Okie dokie. How do we clear these slides on here? Let's see. Oh, never mind. I won't touch that. Okie dokie. Let's erase really quickly. So I can show you a couple of diagrams. Sorry for the silence. I don't like it either. I feel like it's kind of awkward, but it's okay. Here, funny joke. What was the name of the poet that loved chemistry? Later on, when you're learning about acids and bases, you'll laugh. His name was Edgar Allan Poe. Get it? P-O-H. Oh my goodness. I made my teacher laugh so hard when I came up with that joke. I am hilarious. Okay, that's besides the point. So, we're going to be going into the Bohr, this is basically all different models of the electron through time. And next is the planetary model, and I don't think I have space on the next page. So I'm going to draw a picture here, and I'll explain it when we go on to the next slide. So in the Bohr planetary model, it literally looks like a solar system because it's a nucleus surrounded by concentric circles is what they call them when they don't call them principal energy levels or shells, because they call them shells as well. So concentric circles. Let's say that we had more space here, we'd be able to extend. And within these concentric circles, you have electrons. In the first one, you can only have 2. Second one, you can have 8. We'll only put 4. And etc. Electrons on the outside. So you've definitely seen this before. It's basically what they put in cartoons when they're talking about chemistry, what they put in magazines, because it's very easy to understand and it's very easy to pick through the picture and denote how many protons, how many neutrons, how many electrons based on the little dots. So let's look at each. Oh, I do have space. I'll just draw it again. So it's often referred to as the planetary model. Why? Because it has a centered nucleus, in this case the sun, as compared to a solar system, with surrounding orbits or circles or shells that house electrons. And these electrons are the planets, in this case, that orbit around the nucleus. Okay. The composition of the nucleus shows the number of positively charged protons and the number of neutral neutrons. Okay, so the nucleus within the planetary model sometimes is enlarged to show something like this. Oop. Erase. To show something like this. Okay, so it's going to be a densely packed circle. Sometimes they'll do like a little magnifying glass thing where they enlarge a certain portion of it, or sometimes they'll just give it to you really detailed. So it'll be one circle, another circle. It's literally just going to look like grapes overlapping. Excuse the awkward silence. I really apologize. I hate it as well, don't worry. Not just you. I despise awkward silence with a burning passion you do not even understand. Because I watch these videos too to help me teach myself. Man, does it suck when they make awkward jokes and it's like awkwardly silent. That's why I just keep talking. It's annoying, but at least it's noise. Okay, they're not going to be touching like this because they're going to be overlapping each other in like a 3D type structure. But in this case, it's just for the sense of the explanation. So it's going to be a nucleus like this with various particles, as you can see, protons and electrons. Oh, snap. No, 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 no. Wait, never mind. Not electrons, neutrons. These usually have a zero within them. Sorry, brain fart. So it's going to be a nucleus with protons and neutrons depicted like little balls on top of each other. And they're usually going to be different in color, and sometimes they tell you the charge, sometimes they don't. And they just let you to figure out how many neutrons it is depending on the name of the atom, because remember, protons are specific to specific atoms, to specific elements. And you can find that based on the readings on the periodic table. So, yeah. Planetary model centered around a sun, which is a nucleus which contains protons and neutrons. Then it has these circles around it, which are in the next bullet. Let's explain that first. The electrons are shown in, as we said before, concentric circles or shells around the nucleus. Concentric means that they're growing in size, or like they enlarge as you go further out, or you get outside each circle, basically. So what do we mean by concentric circles? We mean this. Let's get another color in here. What about yellow? Okay. So, concentric circles. I'm going to draw dashed lines just for the sake of making it quicker and neater. Concentric circles. Actually, there are some questions that I've seen with dashed concentric circles, so I'm not even going to lie. This isn't even not accurate. This is kind of good that I drew it like this. So concentric, getting bigger as you go out. I'm assuming that's what this means because it says notes from like 3 years ago. I just understand the word in that sense. And I hope you understand it as well. So yeah, planetary model, concentric circles. Designated by the letters K, L, M, and O, P, Q, or numbers 1, 2, 3, 4, 5, 6, and 7. So basically, you number the shells going from inside out, or closest to the nucleus to farthest from the nucleus. So in this case, we have circle 1, 2, and 3, or shell 1, shell 2, and shell 3. Does that make sense? I can't hear you, but I'm assuming you're saying yes. So, the first circle, in this case, can hold a maximum of 2 electrons. And the second circle can hold a maximum of 8 electrons. You'll get into how I got these numbers in another lesson, which has to do with quantum mechanics and quantum numbers, basically. And it's all based off the number n, which denotes electrons and principal energy levels and the amount of orbitals within it. It's basically very correlated to the wave mechanical model, which we'll talk a little bit more about later on. Okay. The outermost electrons are called valence electrons. These are super important. Please never forget this. Valence electrons. Crazy important. Oh my goodness, you wouldn't even understand. So crazy important, like more important than knowing how to spell. When the valence shell is filled, the elements are noble gases. That's why they're in group 18. Let's just abbreviate NG. Noble gases. Why? Because they have 8 valence electrons, and what's the maximum amount of valence electrons an element can have? Yeah, you guessed it, 8. Because when the valence shell is filled, it's 8 electrons. And if when the valence shell is filled, it's a noble gas. Therefore, the maximum number of electrons a valence shell can have is 8. That was super fast and did not make sense, but it'll make sense when you talk about quantum numbers. I promise. Okie dokie. When a blank is filled, the next element begins to fill the next energy level in the higher valence shell. So, when a shell is filled. So, these circles are referred to as principal energy levels or shells. I personally, from my understanding, refer to them as shells because when our teacher taught our curriculum, he taught it along with the wave mechanical model and quantum numbers and quantum mechanics. So all of this was bunched together, but in general, it's not taught like that because quantum mechanics isn't really needed. It's just basically for your knowledge. But when you refer to one of the circles outside the nucleus as a circle and not an energy level or a shell, it's very difficult to understand that electrons are never in a certain place. They're always in a general area or in between two boundaries because they're not set boundaries. They're like, what's it called? Running hills or slowly softly sloping hills. It's very, very difficult to understand and visualize because the atom technically is all energy and it's basically like a wave and not a specifically like bound object. And it's very difficult to understand because in this case it's getting onto a very small scale, and this is where things get weird according to my physics teacher this year, because the microscopic world is weird, but the atomic world and the molecular world is even weirder because that's when rules start not coming into play. And all of this is very abstract because that's why we usually refer to the Bohr's model currently, because it's so easy to understand. But then once you get into the wave mechanical model, it makes virtually like no sense compared to the use of orbitals and all that. So I'll draw, when I'm doing the wave mechanical model, an example of how I visualized it and was able to understand it in like a snap. But for now, let's keep on going. At this point, we're at slide 7 out of 14, and my throat is crazy dry. So I'm going to take a drink. Excuse me. Okay, let's proceed. So as I was saying, the wave mechanical model. This modern model of the atom pictures the atom as having a dense, positively charged nucleus as proposed in the planetary model. So the idea carries on. The atom has a dense, positively charged nucleus because since neutrons have no charge, it's technically all just positive charge that's present. Okie dokie. Electrons with distinct amounts of energy move in areas called orbitals. This is where the confusion begins taking place. So electrons are moving within the atom, and it's taken account for within the planetary model that the electrons move within the circles. So you know that if an electron is here, it doesn't matter in what direction, but it's understood that it'll be moving. And it'll be here in a few seconds, or in a few moments even, not complete seconds. Then it'll be here, then it'll be here again, then it'll be here. It's understood. But within the wave mechanical model, you have a nucleus, energy level 1, so it's between here, energy level 2, between here. And let's say we have an electron in here. So it's in here 1 second, and it can be here the next, and it can be here, then here, then here, then here. But they're moving within this general area. But it's not even like that. Like, it can't even be explained in the sense that it just moves randomly, because it doesn't. So remember how we said there can only be 2 electrons in the first energy level? Well, that's when orbitals come into play, and it's completely different because the orbital is basically what the energy level is, but sometimes it doesn't take it up completely. It just does not make sense very easily. It's a very abstract thought. And right now I'm flipping through my notes trying to find the picture I drew that made me understand it. So give me 2 seconds. Okay, so it turns out I left my page of notes from 2 years ago in my AP chemistry binder, which is conveniently at school and not here. So I'm going to do my best to explain it. So we know that the first energy level can only have 2 electrons, as stated by the previous slide. And I'm not going to go too deep into this because it's very confusing. And this will be explained further along by your teachers because it's not necessary for the curriculum, but it's just very difficult to understand. So you have 2 electrons in the first energy level that are within an orbital, right? So each orbital, this is a side point of information, can only hold 2 electrons. But there are different types of orbitals, such as s orbitals, p orbitals, d orbitals, and f orbitals, which can all hold different amounts of electrons. That's not necessary for you to know currently. That's only if you take AP Chemistry. But now that you know that there are different types of orbitals, so let's say the first orbital here can only hold 2 electrons because that's the maximum that the energy level can hold in general. Therefore, you'll have an orbital that can only hold 2 because that is the minimum amount of electrons any orbital can hold. So you have, so in the wave mechanical model also, electrons are represented as up and down. So we have one up and one down. Facing inward toward the nucleus is down, for facing outward is up. We can just leave it as that. So within this energy level, you have one up and one down. In the next one, since the maximum is 8, let's fill it up. So we have one orbital with 2, because you always have to start with what you started with over here. So it'll be one up and one down. Then you'll have one with 3. Up, 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 down, down, down. So we filled this orbital. So now, you see how these are like touching? This is only because this is a different type of orbital which can hold 6. But it's made up of groups of 2. So it's very, very difficult to understand in this sense, but this depiction of it is what helped me understand it. Because within each energy level, there's different areas for electrons to be located, and they travel in different size groups. But I don't know if this really makes sense, but it's basically just an introductory explanation of the wave mechanical model and how orbitals work and all that. It makes sense once it's explained to you in one whole lesson, but since this is basically a whole bunch of little lessons explaining the atom in general, I don't want to get too deep into it, even though I already kind of did. So let's continue. Electrons with distinct amounts of energy move in areas called orbitals. And an orbital is described as a region in which an electron of a particular amount of energy, this comes in handy later on, and I'll explain why, is most likely to be located. So again, electrons are never in one single spot. They're in a general area. Next slide. Subatomic particles. Boop, 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 boop. What happened to that bottom bullet? Wow. Interesting. I apologize. Okay. So protons, they're located within the nucleus. They have a positive 1 charge. Their symbol is either P plus, or it can be P1 plus. plus 1. We rarely use this one. This is definitely what you'll see most of the time. And AMUs are atomic mass units. And the proton is the standard for atomic mass units. So therefore, 1 proton equals 1 atomic mass unit, basically. So next is neutrons, and those are also located within the nucleus. They have a 0 charge, which is neutral, and their symbol is either N, 1, 0, N, or N0. We rarely use this, and we rarely use this. This is what you'll see most often. And again, mass is equal to 1 AMU, which in actuality it's 0.997, but we round up to 1. And protons and neutrons are relatively similar in mass, and they constitute the mass of the atom. So that's why it's just considered as 1 AMU instead of the 0.997. And electrons, they are -1 in charge. They are not found in the nucleus, and in fact are found within orbitals surrounding the nucleus. And this is attributed to the derived wave mechanical model from the planetary model. I'm just going to continue on this slide talking about the subatomic particles because it got cut off. But the wave mechanical model, as opposed to the planetary model, has general areas of electron movement instead of concentric circles or principal energy levels, which are denoted by rings. And these orbitals eventually become known as electron clouds. It's very important because electrons, when they move freely, create electricity, and the electron cloud is basically free-flowing electrons in a general area. Very important to remember. And the symbol for an electron is either negative IB, or this is that special beta B, or just beta. We rarely refer to it as this, and just as -E, but you'll see this a lot along with this. Alrighty. Electrons are also called beta particles, which are negative in charge as well, and can be found within your reference tables. There are 0 AMUs, and in actuality are 1/8000th and 36th of the mass of a proton. So it's 1 out of 1,836 of 1 AMU. That's why we consider it basically 0. It's negligent because of how small the number is. So determining the number of subatomic particles within an atom, atomic mass will be rounded to the nearest whole number AMU in adding protons and neutrons to get the atomic mass. So the number of protons plus the number of neutrons equals atomic mass. Okie dokie, and hydrogen is the only element without neutrons because its atomic number is 1. Therefore, it only has 1 neutron, 1 electron, and its mass number is 1.008. Therefore, it has no neutrons, or else it would be 2. And that's an isotope of hydrogen. Therefore, the general makeup of hydrogen is without neutrons. Next, the atomic number is the total number of protons found within the nucleus of an atom. And the periodic table is set up in the sense that atomic number increases as protons increase, and it's sequential. Atomic number of an element is used to identify its specific type. Basically, You can tell what type of element it is based on its atomic number. So if you see an atomic number of 1, you know it's hydrogen. Of 2, it's helium. Of 3, it's lithium, and so on. Matter is neutral because in matter, protons equal electrons, therefore charge is balanced. So the number of protons equals the number of electrons, and plus ones and minus ones cancel out to give you 0. Basically, no net charge. That's most of the time. Number of neutrons equals atomic mass minus atomic number. Down here. Atomic mass minus atomic number. Basically, atomic mass minus atomic number is basically the combined number of protons and neutrons minus protons, which just gives you neutrons. Okie dokie. We have examples up next. So if you go to your reference table, I'll give you a few minutes to solve this. Basically, in this first example, you're being led by the atomic symbol. So find the atomic symbol of boron, I believe, and fill in its corresponding atomic number, protons, neutrons, electrons, and atomic mass. These that I'm starring, you can find on the little box within the reference table on the periodic table. And these you have to look further into with the little equations I gave you, little subtraction and addition, and just knowing what this and lists and is composed of and what it means. Because once you know this, you can automatically fill out another category. I'll give you a hint. Atomic number equals the number of... Poop. I'm not going to tell you. Figure it out. At this moment, you should pause the video and fill out the problem set within your notes along with your teacher, or if you're studying by yourself, fill it out within your notes or on a set of loose leaf paper, and we'll make sure to go over it. Okay, so hopefully you've paused the video, and I'm going to fill in the answers for the first row. So boron has an atomic number of 5, with atomic number equaling the number of protons. The number of protons equals 5. Neutrons equals 6 because the rounded mass is 11 right here. So protons plus neutrons equals mass. And the number of electrons can be figured out by the electron configuration, or it's just equal to the number of protons because it's all elements are basically neutral. So 5. Now that you saw how I solved the first one, you probably solved the next few the same way. So atomic number 11 is sodium. So you have an A over here with 11 protons. Atomic mass is 24, therefore 24 minus 11 equals 13. 13 neutrons, and you have 11 electrons because it's equal to the number of protons. Over here, you can just match it up with 31 electrons because the protons are equal to 31. Protons equals atomic number. So what's number 31? That would be gallium, Ga, and its atomic mass is about 70, 69.7. Okie dokie. Next slide. Ions. Woohoo. So, atoms where the number of protons is not equal to the number of electrons, resulting in a positively or negatively charged atom. Here we go with that abbreviation symbol. So it's not equal to the number of electrons. So I'm going to tell you before we even continue reading, protons never change. The number of protons will never change because that will be changing its atomic number, and it will mess the whole periodic table up. Therefore, protons never will ever change. Ever. Like, ever. Okie dokie. So, the atomic number of an atom identifies it as a specific element. If the atomic number changes, so does the element. Same for both. Ions can only be formed through the gain or loss of electrons, but never by the gain or loss of protons. I'm just going to put plus or minus for gain or loss. So here are some examples. Let's clear the board. I'm going to give you two examples of one single element. Specifically, we're going to use oxygen. So we have oxygen and oxygen 2 minus. So oxygen, atomic number of 8. Remember, protons never change. Therefore, that'll be the same for both. Now, neutrons, since the mass number is 16, will be also 8. And remember when I said that the change in electrons, as we said that were ions, a change in electrons is basically negligible because of its small mass. That's why the mass is the same. And electrons, in this case, it's a perfectly stable atom, therefore protons equal electrons, and it'll be 8 electrons. And in this case, 2 minus means it's a negatively charged atom, therefore there should be more negative charge, more electrons. So 2 minus is 2 charges more than it was when it was stable, therefore it has 10 electrons. One more example and we'll move on. I apologize for my heavy breathing. I really, really do, but I'm like out of breath and parched. Oh my goodness. Okie dokie. Now we're going to move on to calcium and calcium 2 plus. So, atomic number of 20, therefore protons equals 20. No change in protons ever, therefore this equals 20 as well. Neutrons, mass is 40.1, I believe, actually. So, 40. Mass doesn't change. Oops, sorry, this is supposed to be 20. 20. And then electrons is equal to 20 here because protons always equal electrons in stable atoms. In non-ion atoms. And in this one, since you have 2 less negative charges, you will have number of electrons of 18. A positive charge on an ion indicates a loss of electrons. Okay, next slide. Oh, I had space for the examples. How funny. We already used it. Hee hee. Now, electrons. Woo woo. So, let's shift in my book over here to the electrons. I apologize. Okay, so electrons. Excited state. A free-floating electron transfers its kinetic energy into an electron found within an atom. So free-floating electrons come from being excited. They're expulsed from the atom, and they're left free-floating within whatever you want to call space. So they're just free-floating electrons. These electrons have kinetic energy since they're moving around, and when they collide with another atom, they usually collide with another electron, giving it its kinetic energy, and therefore exciting that subatomic particle. This increases the electron's kinetic energy and allows it to move to an energy level further from the nucleus. So this establishes the notion that when energy increases, the electrons must move farther away from the nucleus. Therefore, the energy levels closer to the nucleus are of less energy, and the ones farther away are of higher energy. Therefore, you find electrons of much higher energy farther away, and electrons of very small energies closer to the nucleus. In an excited state, an electron has more energy than normal and is considered unstable. So the atom isn't usually considered unstable, it's just the electron. But sometimes you'll hear it used coterminally. In order to become stable, the excited electron must lose the energy it gained. So therefore, to return back to its normal state, to its normal energy level, the electron has to get rid of that energy. And the energy is given off as a wave, and this wave is perceived as visible light. So when an electron is returning back to its ground state, basically what it's called is its original state, the ground state, it will emit light. And you can see this actually in neon signs. It's just excited neon gas, and these electrons moving back down to their ground state emit these brightly colored lights, and depending on the amount of energy that the electron has, it will emit a different colored light, therefore different frequencies, and that's why you perceive crazy rainbow colored neon lights. Okay, and that'll be it. So, atomic structure, it varies from concept as planetary model and wave mechanical model speak about basically just content, which is the discoveries and the scientists and their experiments. Know the gold foil experiment and the atomic theory. And in electrons with excited state and ground state, just know that energy must be released in order for an electron to return to its ground state, and this can be emitted as light. And the only way to become excited is to collide with another electron. So thanks for listening, guys. It's been great teaching you, and hope to see you next time. Bye-bye.